Last time I gave you a little preview of the topic of seasonality, which you can again see in this picture here, also taken like the last one in the southern Appalachians, where it is still all but winter in the high elevations in the month of April, although down in the valleys, spring has begun. Now, we're going to investigate seasonality in a little bit more detail, and then we're going to move on and talk about the sun and how the sun is involved in all that sort of thing. And then we will move on to discuss, in general terms, the atmosphere as well. So, in order to do that, let's start out by moving from the southern end of the Appalachians to the northern end. We're now in northern Vermont, also in the same month of April. And if it looked wintry in North Carolina, in the high elevations, it is the dead of winter here, with still 6 to 8 feet of snow in the high elevations. When I was up here walking around, you simply couldn't do it without snowshoes. Now, here we are in the lowlands of Vermont. And you can see that spring is not nearly as far along here as it was in North Carolina. There are no leaves on the trees yet, but still the ice is off the streams, the snow is melted, and the grass is starting to turn green. So not only is there an altitudinal component to how spring proceeds, but there's also a latitudinal component. Now, all this temperate zone business is quite a bit different from what you find in many of the world's tropical regions. Instead of there being 4 distinct seasons, a winter, spring, summer, fall, there are 2 seasons. There is a wet season, which in the northern hemisphere corresponds to our summer, and that's what you're seeing here on the island of Bali, is the wet season. But then there is also a dry season when it rains much less. It may not completely stop raining, depending upon where in the world you are, but you also have the development of lower humidity and the setting up of trade winds, which blow pretty consistently day and night for months on end in these tropical regions. So let's summarize. We've seen that climate can vary not only latitudinally, but also with respect to elevation, with increasing elevation simulating the effects of moving north. Temperate latitudes tend to have 4 distinct seasons, whereas tropical latitudes often tend towards 2 seasons. Now let me introduce the concept of biomes, which we'll be talking about in much greater detail later on. I bring this up now because this seasonality business, the issue of temperature and rainfall patterns and all that, those are the kinds of factors that are used to define biomes. We'll see that there's other factors like soil that are involved too, but this is a good point at which to bring up this topic. Now, seasonality is related not only to latitude, it's related also to the fact that the Earth is tilted on its axis. And this slide here summarizes a few points about the relationship between latitude and solar intensity. Not surprisingly, the intensity of solar radiation decreases with increasing latitude, so that polar regions receive less intense solar radiation than do equatorial regions. This changes the quality of visible light that your own eyes see. Tropical light tends toward the white, whereas northern temperate light tends more towards the yellow. Now, of this solar radiation, which impacts the Earth at any latitude, much of it is reflected back into space. Although a substantial part, about 2/3 of it, actually does get absorbed one way or another. It depends on what kind of surface the sunlight is hitting. Things like glaciers and ice reflect most of the solar radiation that hits them, so they are, in essence, cooling agents for the Earth's surface. They have what's referred to as high albedos because they reflect so much of the solar radiation. Things like oceans and forests, on the other hand, tend to absorb most of the radiation that hits them. Let's look at a graphic that illustrates this. You'll see that much of the light that strikes the Earth is absorbed by the atmosphere itself, by the Earth's surface, and to a lesser extent by clouds. Clouds are actually much better at reflecting light than absorbing it. And a certain amount is even reflected from the ground. Now let's turn our attention to the atmosphere. We're looking here at the troposphere, that region where those low puffy clouds are present, that part of the atmosphere with which we are all intimately familiar, the densest part of the atmosphere where air molecules are most closely packed near the Earth's surface. Well, if we look at the atmosphere overall, it is to a large degree composed of an inert element, nitrogen. So much of what you are seeing here is an atmosphere comprised of nitrogen. Now, in recent Earth history, another big chunk of the Earth's atmosphere is composed of oxygen. Oxygen wasn't a component of the early atmosphere, but due to life processes, you might consider what life process that is that releases oxygen as a waste product. But due to life processes, oxygen has become a principal component of the atmosphere as well. Then there are a variety of lesser gases that make up only a tiny proportion of the Earth's atmosphere. We can summarize some of these facts like this. Oxygen is 21% of the Earth's atmosphere, whereas nitrogen is 78%. That adds up to 99%, which still leaves 1% to be accounted for. Much of that 1% is made up of gases like the inert argon, neon, helium, but also carbon dioxide, which we'll discuss quite a bit in episodes to come. You might consider where much of that carbon dioxide might come from in the atmosphere. Think about what happens when you breathe out. And the other important component gas is water vapor. One last thing to note would be how it is that the atmosphere shields the Earth from high energy solar radiation in the form of ultraviolet rays, X-rays, and cosmic rays. We will be discussing that in more detail as well. Now, the Earth's early atmosphere was not at all like this present atmosphere we have. It was a bit more like what might come out of these sorts of things here, these volcanic cones. We're looking here from Mauna Kea on the big island of Hawaii across towards Mauna Loa, the other massive volcano that makes up the big island of Hawaii. The white stuff in the midground there is clouds. We're looking down on the clouds from the highest elevations. The clouds are that area under which rainforest develops. But once you get up really high, you're above that rainforest zone into a rather dry, not quite desert-like, but rather dry and cold environment. So, the very first atmosphere of the Earth, when the Earth was very, very young, would probably have been primarily hydrogen and helium, the two most abundant gases, two most abundant elements, in fact, in the universe. But these are light elements and would have dissipated, evolved off into space to a significant degree fairly early on. And so that first atmosphere would have been replaced by a second atmosphere that would have included many of the kinds of gases that come out of volcanoes, things like water vapor and methane and sulfur dioxide and a variety of other gases. Now, one thing about an atmosphere that's comprised of those kind of gases is that it is referred to as a reducing environment. It's an environment that gains electrons. If you are familiar with the term redox reactions, it is a reduction environment as opposed to an oxidizing environment. We'll talk a little bit more about that in the next slide. It wasn't until life appeared on Earth that this second atmosphere would have started changing. The presence of life had a fundamental impact on the Earth's atmosphere. The presence of free oxygen is a consequence of photosynthesis. And that conversion of the atmosphere from a reducing environment to one in which oxygen was present, it became an oxidizing environment, an electron-losing environment. Now, exactly what the composition of the early Earth environment atmosphere was, it's a subject of continued debate. The ideas on all this have changed over the years, but the generalizations that I'm making here will likely hold up reasonably well. So here's a summary of some of that information about the early Earth atmosphere, the first atmosphere being comprised of principally hydrogen, helium, and the second atmosphere being comprised of a more diverse variety of gases, which to a significant degree would have been of volcanic origin. This is where we can talk more about the idea of a redox reaction and the idea that the early Earth atmosphere was a reducing environment. If we think of an element like oxygen, oxygen is an element that in chemical reactions tends to gain electrons. It pulls them away from other things. The thing that loses the electrons to oxygen is referred to as being oxidized. And oxygen, which gains the electrons, is referred to as being reduced. So this early atmosphere would have been one in which electrons would have been gained by it. Now, once we have an oxygen atmosphere, once photosynthesis begins and we have an oxygen atmosphere developing, which still, by the way, was fairly early on in Earth history. We're still talking about well over 1 billion years of oxygen atmosphere on Earth. Then you have an environment in which oxygen is pulling electrons away from other things. So now it becomes an oxidizing environment. Things are oxidized by oxygen. And that is where the term redox comes from. That's shorthand for oxidation reduction reactions. Now let's head back to our present atmosphere. Notice that we are pretty high up here. We're traveling in a jetliner at about 30,000 feet. And so we are actually looking down on the lower Earth atmosphere, the troposphere, where you see all those white puffy clouds. And we're looking directly into an upper layer called the stratosphere, which extends upward of 50 kilometers. It is a layer that is characterized by a steady wind, by comparatively uniform temperatures, although because of the presence of ozone molecules, 3 oxygen atoms joined together, the temperature of the layer actually starts rising with elevation because ozone intercepts ultraviolet radiation, and as it absorbs that radiation, that high energy radiation, that energy starts increasing the temperature. Now, as we look at the very uppermost part of the slide, we're looking towards a darker area. As we look up, we're looking into the mesosphere, which is a very upper envelope of very thin air that extends upward to 80 kilometers. And here it gets very cold. And then above that, there is still more atmosphere, the outermost envelope of atmosphere, referred to as the thermosphere. This is the layer that extends upward close to 500 kilometers above the surface of the Earth. Very thin air, but in a layer that is capable of absorbing X-ray radiation, among the highest energy kinds of wavelengths that strike the Earth. And so this raises the temperature of the thermosphere extremely high. So let's summarize some of these points. As we look down on Agiguan Island in the Marianas Islands of the Western Pacific, we're looking down through the troposphere here. You can see those puffy clouds right beneath me in this picture. This was taken from a helicopter. So we're not flying up very high here. So we see that the troposphere again is the lowest layer of the atmosphere. It does get cooler with altitude. It also gets thinner. The molecules become further apart with altitude. This is the layer in which much of the Earth's weather occurs. Above that, the place where jetliners fly, is the stratosphere, the layer in which ultraviolet light is intercepted by ozone. Then above that, we have the mesosphere, which, as I said, is a layer in which it gets very cold. And then the uppermost layer of the atmosphere, the thermosphere, has temperatures that are in the range of 1,000 degrees Celsius as it intercepts all that high energy X-ray radiation. The thermosphere is also notable in that it is the place that reflects radio waves. So from radio stations broadcasting signals, those signals bounce off of that upper atmosphere layer without the need for satellites. It is also the place in which auroras occur. If you've ever seen an aurora, if you live in the far northern latitudes, you see them more frequently. So if you live in northern New England or Canada, you see them more frequently than you do to the south. Although in the wintertime, you can even see them fairly far south. Auroras are a consequence of high energy radiation striking that upper atmosphere. Here's a graphic that illustrates that layering of the atmosphere in a little bit different way, showing the relationship of the layers and the fact that the troposphere is a relatively thin layer, whereas the thermosphere is the widest, outermost layer of the atmosphere. Now let's talk about that thing that goes on in that lowest troposphere layer of the atmosphere, weather. And let's distinguish between the term weather and the term climate. Weather is what you see going on in this picture. I took this picture several years back during what was one of the coldest winters we ever had here in southern New England. The air was so cold that the water vapor from this river rapid area was freezing in the air. You could actually feel your own breath crystallizing and blowing back on your face. It was just a bitter, bitter winter. But that was the weather that went on for a few days. It was what happens at a given place in time in terms of what's going on in the atmosphere. That is in contrast to climate, which refers to the prevailing weather of a geographic region. So here in southern New England, we do have colder winters than we do in the southeast of the U.S., but still they are comparatively mild if we look at our winter temperatures with those of, let's say, maritime Canada. So prevailing temperatures, prevailing patterns of rainfall, things like that. It certainly varies from year to year, but when we look at it on average, we can get a picture of regional climate. This slide summarizes that difference between weather and climate, pointing out that weather is what happens at a given place in time, whereas climate is what happens over, let's say, a season in a particular geographic location. So we might talk about the winter climate of southern New England, or the summer climate of East Texas, or something like that. The slide also makes a couple other points worth mentioning here. It points out the term precipitation. This is a phenomenon that happens when warm, moist air rises and cools, which results in the moisture in the air condensing into water droplets. You're seeing something like that happening in this picture here, especially in the background, where you have comparatively warm air directly over liquid water, which then, as it rises, freezes, in this case, not to water droplets, but to ice crystals. And you're actually looking through a haze of ice crystals in this picture here. So when water vapor in more typical kinds of situations, perhaps than this, rises, it tends to accumulate a little higher in the atmosphere, and that's what, as it cools and condenses, forms clouds. And of course, when the clouds become heavily laden with water droplets, that's released as rain, or in the case of wintertime, snow. One of the phenomena that results in air picking up moisture is air moving across water. And again, you can see that happening right in this picture. Another phenomenon that this slide points out is the rain shadow effect, and we'll take a look at the consequences of that momentarily. It is a situation where, as prevailing winds move, let's say, off of the Pacific Ocean towards the coast of North America, prevailing winds in North America are from west to east. Well, they strike the coast of California and immediately encounter mountains, and so they start rising above those mountains. As they do, they cool, the moisture condenses, and it's dropped in the upper elevations of the mountains, so that by the time those air masses pass to the east of the mountains, they're relatively dry. And that leads to what's referred to as the rain shadow, where that very dry air has nothing left to drop on the land below it. So let's look at a picture of that. That, by the way, is referred to as the leeward side of a mountain. These are the San Gabriel Mountains, behind Los Angeles in Southern California. This is the windward side of the mountains. This is where wind from the Pacific Ocean is first intercepted as that air rises in these mountains and cools. The moisture in the air condenses and it's dropped as precipitation, which gives rise to this relatively green landscape you see here. It isn't what I would refer to as a wet landscape. We'll learn later on that this vegetation is actually referred to as chaparral vegetation. There is a distinct rainy season in this area, but we'll come back to that when we talk about biomes. But what precipitation there is in the air is dropped on this side of the mountains. And let's see what the landscape looks like when we get to the other side, the leeward side of the mountains. Well, look at the difference here. Now we are in the desert. Once one comes over those mountains and down the other side, this is what the landscape is like. Now you are into sagebrush and Joshua trees, those scattered tree-like things that you see in the mid and background of this picture. Note also, however, that the sky is absolutely black in this picture. As it turned out, I was in the desert in June on a day when there was a rainstorm, and it was a giant rainstorm. Thunder, lightning, pouring torrential rain. It's the sort of thing that does happen at that time of the year in the desert. You do get the occasional big rainstorm, and I just happened to be there on that day. Also, these deserts are high deserts. And so, although it was what I should say is usually very dry here, it was kind of cold. Even though it was June, I was wearing a jacket out there. Let's look at one more picture so that I can introduce the next topic of atmospheric circulation. We're looking here at a common raven who is using the phenomenon of the onshore breeze, that differential in temperature between water and land that drives movement of air from water to land as the land heats up. He's riding that breeze and illustrating for us some of the phenomena that are associated with atmospheric circulation. We will be talking about the phenomenon of convection, which is really related to what he's doing right here, where you get the development of this motion of air as a consequence of differential heating, so that the less dense warm air is rising and the denser cool air is moving in to replace it. We'll talk about wind and exactly what it is that wind is, and a phenomenon called the Coriolis effect. And one last thing that we'll be taking a look at in this next slideshow will be the topic of prevailing winds on different parts of the planet.